Hello.
Fantastic. We are winning. How are you doing, Conrad? I was just checking. I wasn't sure if we had attained takeoff just yet, but it's good that you can.
Yeah.
Important. Good. Right. So, moment of reckoning. It's all happening tomorrow.
Yeah.
Oh,
It's all happening tomorrow. Yes.
what time do you have?
Oh, sorry, my being very slow.
Don't worry. Are you on study leave at the moment? Then is that what's going on? Is that what they've given you?
No, not study leave yet. It's after half term, which is a bit odd, but
That is very odd because they expect. So when was the last time you? So literally, you've been having lessons and then, boof, you're going straight into an exam.
yeah,
I think that's very, very unfair.
it's yeah, I think yeah. I mean, we're still required to show up to lessons before.
I know, and you're still being given homework and you're still learning new material as well.
Yeah, which is really annoying.
Oh my days, right. Okay, so yeah, you've got it cut out rough against you, unfortunately. But this is one of those subjects where if I could use the term, they like to separate the men from the boys, okay? which is which is rather important because at times you have to think to say, are you testing me for knowing the material, or are you testing me for my ability to handle a stressful situation? Which is it? What is the aim of this assessment? And just to make you feel a little bit better, I'll give you a bit of a narrative when I was back at Cambridge, which was an absolute culture shock because we had exams over 2 days. So a 3-hour exam in the morning, 9 till 12, and then 1 till 4, and then the same the next day. That, when I finished, I've never ever done anything like that in my life. When I finished, my hand was spasming as if I'm suffering from. I'm not joking, Conrad. My hand was shaking like I suffer from Parkinson's disease. Literally, for a week, my hand was just doing this. Just that. And I was like, what is going on here? So we complained massively and just said that was, you weren't intending to test us on our intelligence. That was just, how can we work?
That was like,
torture,
how strong
absolute
are the
torture.
muscles in your hand?
Yeah.
I once had 3 exams.
Yeah.
One day I had a physics exam, which was an hour and a half, a philosophy exam, which was 2 hours and a half, and an art exam, which lasted the rest of the day. And it was the worst. It was the worst stuff.
Painful.
I can't tell you enough how awful that day was. It's because I take the weirdest range of subjects. They like, oh, no one's gonna have these subjects, so.
Okay, so you have been through the baptism of fire, then it seems. So that's good. At least you've got something to work off.
Exactly.
Right. Excellent. So what we're going to do then, Conrad, today we're just going to focus on the paper. And what I wanted to find out from you first is, have you done any practice under time conditions yet?
I'm not sure about time conditions. I've just been doing practice. I have been doing practice papers, but not specifically under time conditions.
So I would strongly urge you. That's the reason why it dawned on me. I suddenly thought, you know what, 6:30. If he has not had a chance to go through a time session, if we start at 6:30, that's not going to leave him a lot of time. So it's better we start early, and then that leaves him a little bit more time in the evening. So that was part of my motivation, but I thought I could relay that. Okay. So we're going to look through some questions from a paper, and the recent paper I came across. Well, there is a 2021 paper, but it's not in the public domain. And in all honesty, my feeling is they are going to cannibalize questions from the 2021 paper and maybe a few from other segments or other sections and such. So it would be good to do a paper that you've not seen, so you really know where you stand. So even if I had access to the 2021 paper, it would not be, it would nullify the whole exercise if we went through the questions for the exam. So it's we are on a level playing field, and we really are trying to gauge what progress have we made. So this is a 2020 paper, full paper. You've got the multiple choice, but also you've got the long structured questions. So to start off with, let's try and simulate as best as we can what you will encounter. Have you done this paper before I even go further?
I don't think so.
Even better.
I don't think so.
Even better. So when you're ready, Conrad, you are going to need your calculator. You need your data sheet. Do you have your data sheet and your
Yes.
We have a data sheet as well. Awesome. So we're good to rock and roll. Yeah. So when you're ready,
yeah,
and as best as you can. So here, please note you have 25 minutes. So they're giving you about a minute and 15 seconds per question.
Yeah.
Now, as a little strategy, which you can't adopt in this particular instance, and I'm going to give you a bit of a strategy that is really, really good to use so that you can maximize this 25 minutes. Please, please, please do not answer these questions in accordance to, going from 1 to 2 successively like that. Don't.
Yeah.
Because there are some questions that are going to take you more time to think about than others. Answer the wordy ones, the ones where there are no calculations involved. So number 1, great candidate. No calculations involved. It's just a clear recall. Tick all those. Yeah. Those are going to take you a few minutes to do. Then go and do the tough ones where they're numbers. That is what I would suggest that you do.
Yeah. Okay. Yeah.
Yeah, because students sometimes spend a lot of time and then they lose time to finish off and then end up guessing the other, which is not a good strategy. Right. So sorry you can't do this because you don't have the paper, but let's just remember that in the back of our minds for tomorrow. Is that okay?
Yeah.
Cool. Yeah. When you're ready then, Conrad, all yours.
Yeah. So I'm thinking, would it be charge for the first one because Q equals IT?
Good start. Good start. Absolutely spot on. Good.
A2. Should I just do it?
We're just going to do it one.
Should we just do it in order?
Kind of thing. But I know that in the exam, like I say, actually, you know what I might do, Conrad? Easy thing to do. Yeah, because we need to try and simulate the situation as best as possible, really, extents. I will send you the paper, okay?
Yeah.
And then that way you can choose which ones you want to start off with, or sorry.
Should I print it out?
If you've got a printer accessible, that will be fab. Do you have a printer accessible?
Yeah.
That is awesome. Awesome. Awesome.
Just hope.
So there we go. I'll send this to you now. As boom bop and but up. Done.
Inbox. Did you send that to my oh, here it is. Yeah. Yeah. File. Print. Decided. No. Let me open it. Docs. File. Print. I don't know why it's only saying it's got one page.
Okay. Alternatively, you can just scroll through the questions and then have a pick, and then I'll tell you which ones are outstanding if you like.
Yeah. All right. Yeah. I guess I'll just go look on this then. I'll go straight. I guess this one has no calculations. Number 3.
Number 3, good man. Let's go straight to 3 then.
Yeah.
3, yep. One to think about. Cool. No calculation involved. Literally just thinking about the scenario.
Yeah. All made from scratch. Paper is dropped from it. Each time velocity before it hits the ground. If it reaches terminal velocity. Guess it would be would it be B?
Okay, B. Yeah, go on.
It reaches terminal velocity before it hits the ground. So it accelerates and then it sort of plateaus if it but would it be so that means the acceleration is increasing, then the acceleration remains constant. Would it be D or not?
Okay, so take your time. When faced with a question like this, okay, just how to think around the problem. I'm going to give you a bit of a hint. They have plotted an acceleration against time, yeah, which is rather unusual. You don't normally plot for terminal velocity acceleration against time. So what you need to ask yourself is, and this is a graph you would have seen, what does the graph for velocity versus time look like for an object that is going to achieve terminal velocity? And why are you thinking velocity? Well, because you know that the gradient of a velocity time graph gives you acceleration. Then you can start thinking about which of these graphs best interprets that situation. So can you remember what a velocity time graph looks like for something that reaches terminal velocity?
Yeah, so the velocity increases and then once it reaches terminal velocity, it
plateaus, doesn't it? Very good. That is the key understanding here. Very good. There we go. It does this. Spot on. Spot on. Very good. So now we can now start thinking about the acceleration. Well, this portion here has a straight line. What's this telling you about the gradient of this portion? Is it constant or is it changing?
Of B?
No, just of the portion between the red lines, in this green portion between the red notches.
Wait, what? I'm a bit confused.
Can you see my board?
Oh, right. I was on the email.
Sorry, that's why. You can go back to it.
Wait, sorry. It's not letting me. Oh, here. Oh, okay, yeah.
Awesome.
That's constant. Well, that's just acceleration.
Yeah, but what can you say? Is the acceleration changing in this place or is it constant?
It's constant.
Very good. It's constant. So you're getting a feel for the problem. Now, what about here as it starts bending at that point? What's happening to that? Is it decelerating or is it still accelerating?
It's still accelerating, but not at the same rate as it was. It's
much slower rate. So we say deceleration because it's at a slower rate. Now, when it flattens out and it plateaus, what is the acceleration here in this portion here?
It's just it's not accelerating.
Very good. So the acceleration is zero because remember what we said. It's the slope of a velocity time graph. Here I have a slope. Here I have a slope. Here there is no slope. A horizontal line, slope is zero, and it's a horizontal line. Slope zero means zero acceleration. Which of these graphs best fits that bill?
Would it be just the constant acceleration? I guess
think about it here. Acceleration, we said, is constant. Constant acceleration means it's constant. Here it starts decreasing, so it's got to go down.
Oh, so it must
here
be
it's zero, so it's got to come down to zero.
Oh, I see. Yeah, so it must be C.
Correct. Spot on.
Okay, that's definitely made it easier.
Okay, so we started off from a VT because we realized we're not very familiar with what an acceleration time graph looks like. It's not something you see in a textbook given. So we had to work off the knowledge that we know. And one thing we certainly have seen since GCSE is what the velocity time graph of an object that's achieving terminal velocity looks like. So that we know.
Yeah.
Are you okay with that? Okay, good.
Yeah.
Good. It's good to talk through these things anyway. Thought process is good to talk through. Okay, number 4. Oh, sorry. You choosing. I forgot.
Okay.
My apologies.
We can go to 6.
Yeah, cool. All right. Number 6. Yeah, go for it.
Which
I love it. You literally, you're absolutely doing the right thing. And so when you get your paper tomorrow, the first thing you do is, I know everybody's going to pick the pen and they'll be rushing and you feel like you're falling behind in time. Take the paper, just literally just take a minute and tick off the multiple choice that you're going to do first, and then also read the rest of the questions. Do you know why I strongly recommend to just have a read of the questions, even though you're not going to solve them? Just spend the first 3 minutes just reading the questions, formulating a strategy. It feels like a waste of time, especially when Charlie next to you on the right-hand side is busy writing frantically and you're going, I should be writing something. Don't worry about them. Do not worry about them. Now, the reason why I'm telling you to do that in those first 3 minutes is because the mind is an amazing machine. As you're reading, it will know which of those questions you are going to find challenging. And so when you move away and start doing the multiple choice questions, your mind will be processing how to tackle some of the other questions, the challenging ones. So when you actually get to them, your mind has seen them and your subconscious has already been formulating what's the strategy. And it is a subconscious, so you're not going to be conscious that it's working, but trust me, it will be working behind the scenes. Okay, it's a little bit about knowing as well with these things, you know. It's called metacognition, which means thinking about how you think. Okay.
Oh, okay, that's interesting.
Absolutely, so just keep that in mind. It's not something that teachers will tell you, but it is so important. And in my university years, that saved me massively. Right, number 6.
Okay. So I know that a progressive wave does transport energy through space. A stationary wave should have at least one node, I believe. For both waves, the amplitude of the oscillation is the same. I don't think that's true because the amplitude can change.
You're absolutely right. Your facial expression said it all, literally.
Yeah.
How did you also know this, Conrad? It's amazing that if you show like a pet, like a dog, a video of something that violates the laws of physics, or if you show them a video of something that violates it hits them. They look at it weirdly. They go, what? Like literally scientists have been doing tests. So apparently dogs are the best physicists of all the animals.
That's true.
They pick up on things that just don't align with the laws of physics very quickly. So
I've seen videos of monkeys at the zoo being astonished by magic tricks.
Through
the glass. I've seen that.
I haven't seen that one.
So I'm not sure if that's similar, but
it's very similar. I'll be looking out for that. Will be one of the things I'll be looking out for on YouTube tonight. Then, brilliant. So 6 done and beautifully so. So next one.
I think the next one would be 14.
14. Okay, yeah. All these are laden heavily with calculation. So 14, I think, is a fairly good candidate, and I would agree with you.
Yeah. So a seabird dives vertically into water. The seabird is briefly stationary at its greatest depth. In water, the upthrust on the seabird is always greater than the weight. Yep. Which statement is correct about at the instant? The seabird experienced the greatest drag. I'm not sure. Seabird has an upward acceleration. No, thrust on the seabird is equal to the drag. The weight of the seabird is equal to the drag. if it's stationary in if it's briefly stationary, the weight, I guess, the resultant force must be 0.
Okay.
And the weight must, but sorry, my app was just.
So that's okay, Conrad. So just take your time, and I'll give you a bit of a hint here, pointer to help you out. Underline keywords, yeah? Dives vertically. This might be useful to know. Briefly stationary at greater depth.
Drag.
Up thrust.
This is up. Would it
always greater?
Yeah. So it's not D.
Definitely not D.
It says in the question, yeah. The up thrust on the seabird is equal to the drag. Should have an upward acceleration. The acceleration is greatest drag. This one's tricky.
Okay, and to help you out here, sometimes even just a little diagram does help. Okay, if you ever faced with a tricky problem, just say, okay, I'm gonna draw a little diagram here, and you're an artist, so you can draw way better than me. That's my version of a bird, and it's driving down vertically. Okay, there we go. Okay, and that's the bottom of where it comes to a standstill. Okay, so
would yeah, maybe since no, cannot be. Oh, has it frozen?
No, I can still hear you. Sorry, it was just me silent. Sorry. I was just trying to, that's okay.
Is it either A or B?
A or B, the seabird experiences the greatest drag. Okay, so let's analyze A. That's okay that you've thought about and whittled down to these two. But let's just consider the pros or the benefits of each one. The seabird experiences greatest drag. Okay.
I guess
now, how does drag come into this equation? Now, I'm just going to give you something here that you need to remember. Drag, okay?
Yeah.
How much detail should I go? I'm just trying to think how much detail I should go into this. Okay, still worth you knowing, because otherwise it helps you understand the problem better. In a situation where we have a streamlined object moving in a fluid, air or gas, there will be drag. And if it's streamlined, yes, and there is what we call laminar flow. Now, I'll give you an example of what I mean by laminar flow. So imagine you have, let's imagine a bullet. There we go. And these are the streamlines that flow around it. This here is an example of what we call laminar flow. And here, the drag force is equal to, drag force is proportional to the velocity. And that is why when we look at that graph of terminal velocity, it looks like this. It explains it. It is assuming that we're going through what we call laminar flow. So as the velocity increases, the drag force increases proportionally. And that is why,
if it's stationary, then drag shouldn't be.
Thank you. Shouldn't be present.
Okay, so it's
there's
not that
zero.
one.
So it cannot be that one. Also, just to give you a little bit now, again, a deeper insight. So if you don't remember this, I won't blame you, and it won't be the end of the world. Now we have something known as turbulent flow. So during turbulent flow, the streamlines of air look like this. They're broken up and in random. Now this thing is moving extremely fast, super fast. And in this case now, drag is directly proportional to velocity squared. So either way, without you having to remember these two facts as they are turbulent flow or laminar flow, as long as you can just remember that drag has a direct proportion or relationship to velocity, that's good enough.
Yeah.
That itself is good enough. Okay, so A is out of option,
yeah.
with.
So when a force acts on an object, it accelerates it. And since up thrust is a force which is greater than weight, the resultant force is acting upwards. So
yes.
Would it be?
Yeah, go on.
Could it perhaps be B?
You're right. The answer is indeed B.
Yeah.
And the other additional reason to add to that is that for this bird to reach the bottom, what must it be providing? It must be providing, if you like, a forward force, a driving force. It must be providing a thrust, not an up thrust, but there must be a thrust. And for it to reach the bottom, this thrust must be greater than what? Must be greater than the up thrust.
Yeah.
Now it gets to the bottom. So here, at this point in time, if we had to write the equation, let's call thrust T and let's call up thrust U. So we're going to call thrust T and up thrust U. T minus U is equal to MA. Now we've used Newton's second law to say the resultant force is equal to mass times acceleration.
Yeah.
When it gets here now, at the bottom, is there any thrust?
When it gets to the bottom.
And if I this really in its
full, wait,
yeah, so the bottom of the seabed. And I'm going to write this in its full entirety. I'm going to draw a free body diagram and I'm going to show you the forces acting on it. There's the weight. There's also the thrust that this bird is providing. Then we have the up thrust and we also have the drag. These are the forces acting on the bird. So that's the thrust. This T is the thrust and this W is the weight. And this here is a free body diagram. We sometimes abbreviate it as FBD. If you write FBD in your exam, they'll know exactly that you mean a free body or free force body diagram. Okay, so when it stops, which force disappears? This force disappears.
Yeah.
Which other force disappears? Drag. Because it's proportional to velocity.
Oh, yeah.
Okay. So in terms of the forces now, you have the biggest resultant force when it's at the bottom. And the biggest resultant force will result in the biggest acceleration because the mass of the bird is still the same.
Yeah.
Good. Excellent. Super duper. As long as you understand that, because I know we've never had a lesson on terminal velocity. So I don't know where your gaps are. That's the reason why, sorry, I gave you a bit of a mini lesson around this question.
Well, no, that's great. That's exactly what I need.
Good.
That is exactly what I need. So that is brilliant. Thank you.
Super. Excellent. Okay, choose the next one.
I think 16.
16.
16.
Let's go for it. Why not?
SI unit for electrical charge.
Love it. Yeah. Nice and easy. That didn't take you time, did it?
Yeah.
Not at all.
No.
The Coulomb.
Which pair of quantities are the same? SI.
Take your time. SI unit for electrical charge. Okay, well, it's asking, even though I don't like that one because it kind of says like the SI. SI is the Coulomb.
Yeah.
Electrical charge. So I know why they're allowed to get away with it. They have not said SI base unit.
All right.
If that's the
next
SI
question
base units, then this answer here the correct answer would be the ampere second.
Mm. Yeah.
But they've simply just said the SI unit. So SI units are different from SI base units. So there are only 6 SI base units. Whereas SI units are simply units that we use when we are using these things in calculations. Does that make sense?
Yeah.
Just watch out. It's a very, very tricky one, this, because in an exam, you're going to be under high adrenaline action, and you may overlook this word base. But if they have base, it means you need to remember the 6 SI base units. What are they? The kilogram, second, the amp, the Kelvin temperature, the mole, and 6, we've got, hang on, kilogram, the meter. There's a 7th one, which is the candela for light, but you don't need to worry about this. Okay, but make sure these, you know, kilogram, second, amp, Kelvin, mole. Look at this one. Good question. Have the same SI, they've thrown in that word base. So that's now a completely different question to simply SI units.
Work done is force times distance, and force is kg minus 1 distance. Would it be D?
Spot on, sweetly done. Next one.
It's 19.
19. Onwards and forwards we go.
Okay, so it it has, would it be I wouldn't say is elastic is more, it's like a straight line because it returns back to it.
Okay.
So I don't think it's elastic. It's not elastic. It might, I don't know.
Take your time. Let's rule out the ones that are definitely not. Could it be brittle?
Yeah. No, because then it will break.
No. Could it be ductile?
God, ductile.
If we don't know, what is question mark. Ductile means you can draw it into wires.
I see. Oh, that might be.
Okay, that might be. So I'll put a little question mark. Elastic, what do you think?
Because I've seen elastic ones, and it sort of goes back the exact way it went. So I don't think it's elastic.
Okay. So that leaves you with plastic then, doesn't it?
Yeah.
Okay, now let's just think about this one here. So remember when I did a stress strain graph last time, which looked like this?
Yeah.
And we called this a hysteresis loop.
Yeah.
And we said that the area under these 2 curves represents the energy, dissipated. Sorry, dissipated. Really here you can actually say, dissipated as heat. Now, remember when I spoke about this and we looked at the example of the car tire, which car would you go into? And what is the car made of? What material is it made of?
Made of rubber.
Made of rubber. And what kind of material is rubber? Which of these things fits the description?
It's elastic.
Correct.
Oh, yeah. And then it's when it's sort of extended, it's lost its heat.
So if you had an elastic band, remember you were telling me, oh yeah, when you stretch an elastic band, it gets hot.
Yeah.
Correct.
I completely forgot about that.
Yeah. No, don't worry, but that's the reason why, you know, 2 minds are better than 1. And I can give you some points as to how to think about these things. Excellent. So the answer would be C.
It is elastic.
Correct.
Yeah.
C. So an elastic band behaves that way. Good. Excellent. Oops. Let's take that there.
Yeah. I guess the next one will be 20.
20. Moving on. Cool.
Yeah. 2 electrodes are placed in a liquid. electrodes are connected to a cell. So it's ions which are in the electrolyte.
Yeah.
And direction of conventional current. Oh crap. Completely forgot which way. Conventional current. Positive. Would it travel to the right?
You're spot on. You look to seem a bit
Yeah,
doubtful, but I'll remind you,
yeah,
in conventional current always goes from positive to negative. That is the convention.
Yeah. So it must be D.
It's got to be D, correct.
It's got to be D.
It's got to be.
Okay, so we finished all those multiple choice ones that I've just words.
Good. So we've done that one, so we've got 18. Now, at this particular point in time, it now goes down to which ones am I most confident with? Am I most confident with waves? Am I most confident with? So there's a little bit of a strategy you're planning, and all this with moments. What is it that I really feel I can do very quickly as a calculation?
Yeah.
Choose and let me know.
Maybe the number 13.
Number 13. Let's go for that one. Very. Come on, 13. There we go. 13. Yeah, go for it.
Okay. A driver sees an obstacle ahead of the road at time t and applies the brakes. The velocity against time. So we can look at the reaction time of the driver, which is that.
I zoom in a little bit. Sorry, I'll zoom in for you just so you can read that. Sorry for that.
I've got it on split screen, so I've got the.
Oh, so you can see both. Oh, so you were trying to move. Oh, gotcha.
Yeah. So its reaction time would be 0.5 seconds.
Spot on.
And the braking distance, distance is velocity times time. So it's the area underneath the graph. So it would be 3 times 7.
Sorry, one moment while you're just making that calculation. I'll be with you shortly. 2 seconds.
Might be A. So 30 A.
Sorry, Conrad, I'm back again. Yeah, are we still
is it A?
You are absolutely spot on. Excellent.
Brilliant.
Yeah.
I guess we can
it's that area, isn't it?
Yeah.
Very good. So I'm glad you didn't get caught out because it's easy to get caught out with that one. Right.
Yeah. I guess we can go to 12.
Yeah. 12. Cool.
Yeah. Then the force of magnitude 3.5 acts on the object for 2 seconds. Blah, blah. Force times time. Is that the impulse?
That is the impulse.
Yeah, I don't. Will that even help me in this question?
Okay, I'll give you a bit of a hint actually at this stage. Unless you are going for Oxford, Cambridge assessment papers, entrance papers, A-level, they rarely ever give you information that you don't have to use. 9 out of 10 times, just as a general rule, if they give you any piece of information, you have to use it. When you're going for these other assessments, they try and make you decide what you think is useful information. So they throw in all sorts of things in the question as well, but not at A level, not with standard spec. So just keep a note of that. And so if you're doing a question and you have not used a piece of information, chances are you've missed the trick somewhere.
Yeah.
So first port of call, formula. First port of call should be your formula. What is the link between momentum and impulse? That should be your first port of call.
Times changing V over time. And I can sum equals
by the way, just to help you out, being very cunning here, absolutely cunning. So you have to have your wits about you.
Would I multiply 3.5 by 2?
Okay.
Firstly.
Okay, I like that. Why?
Because it's kilograms meters per second.
Okay.
So per second I'd multiply by 2, so it's a total of 7 newtons. What was my in the object? Well, it doesn't say it's acting to the left and moving to the left is 3.5. I always get confused on these questions because when it says what is the change in momentum, I always don't know how to answer.
It's okay. So here we go. And hopefully this should shed some light on how you go about it. So we know that F, the force acting, a resultant force, is mv minus mu over the time. Yeah?
Yeah.
Let's do the formula here, sorry, T. This here, this quantity here, mv minus mu, gives us the...
I don't think we've ever looked at that equation before.
We have it. We actually, it was the last one we looked at in the last 10 minutes of our lesson, and
I meant in school.
Oh, that's such a shame because it is absolutely vital. But you've got it in your notes, which is just a bit of a reminder. When I went through this, it was key for me to. It's very good. So it's okay, but at least you can go in tomorrow knowing that you know it. So this here represents the change in momentum, and it should, because this quantity here, mv, is the final momentum because of multiplying mass by final velocity. Final mom, and this here is quantity is the initial. Well done, good. So final minus initial always gives us the change. Now, so we know, now if I multiply this quantity here by time, I now get F times T is equal to mv minus mu.
guess you would add the mu equals mv. So I guess you ft plus mu.
So remember what I said? They're being very, very cunning, super cunning. In fact, yeah, they're being ridiculously cunning. So this is an equation. So if this side here, remember what we just said, this represents change in momentum, mv final minus mu initial.
Yeah.
It's an equation. So if this is change in momentum,
yeah,
this also must be change in momentum. It's an equation. They've got to be equal.
That makes sense. Yes. Okay, that makes more sense. So it must be 7.
Correct. They were being very.
That's definitely been cleared up. I'm very glad you cleared up for me because I would have had no clue.
Excellent, excellent. That's what I'm here for, Conrad. That's good that you get it now. Good. They were being super cunning, and
yeah,
in the rush of the exam, even the bright students who know this fact will easily go, oh, change in momentum, I've got to add it to whatever that was. However, if they said, what is the object's final momentum? Then at this point now, you need to say 28 minus 7, which is 0.5 times 2. So the final would be 21 kilogram meters per second, or just 21 Newton second. It's okay, they're the same quantity.
Yeah.
So, and that's the reason why they emboldened this. They put it in bold because they say, read it carefully. We are looking for the change.
Yeah.
So whenever you see anything in bold, oftentimes they're saying, read it again, read it 2 times, make sure you know what's going on.
Okay.
Good.
I definitely will then. We'll just go to 11.
Cool. Yeah, of course, man. Why not do some Archimedes and go into the land of Archimedes and the Greek guys? Go for it.
Well, if it's at rest, then the forces should be equal. At rest, the weight is up there. 6. Am I rush this, or is it 6 newtons because it's at rest? So the weight.
You're absolutely spot on. Excellent. And Archimedes would be happy that his name is his discovery is still being put into the brains of many a youth. Okay. So you're absolutely right. Up thrust is always equal to weight.
Yeah.
When floating.
Awesome.
Okay, good. Super.
We can let's go to 10 because I wanna
let's go for it.
Sort of
cruising on. Number 10.
A uniform beam is initially lying on a horizontal ground, as shown below. It's hinged. The beam is tilted from the angle theta equals 0 to 90. The moment of the weight on the beam is about x, point x, and is m against theta. So, okay. So, I feel like what point?
Should I scroll further down so you see the rest of the?
Oh no, don't worry, because I have it on.
Oh yeah, of course, yes, of course. I realize. Yeah, you just realized. Yeah, cool.
The force is the perpendicular force decreases. Because the perpendicular is getting closer. Would it? I don't know. It feels like it's That's weird. That is slightly weird. It feels. Is it? Oh, I don't know. Because the distance from the weight to the X, when it's getting lifted up, it's getting closer to the hinge. So, but the force also, the perpendicular force must stay the same. So I guess it should just be a uniform, just straight line. Right?
I know, and this yeah, it's easy to think that actually on this one. So to understand what this would look like, let's imagine this was resting at this angle theta. Okay.
Yeah.
Okay. So the weight would still be down here, like so. Yeah. W.
Yeah.
And if I wanted to work out the moment about X, well, I would need to know, sorry, by the way, this here would be theta. Are you okay if this is theta?
Yeah.
If that angle is theta, that would be theta. So if I want to work out the moment, and this, of course, will be kept at whatever half of the full length of this thing.
Yeah.
Good. So for a given angle, my expression of the moment about X is going to be, well, I need to find the component of W that is perpendicular to this distance to X. There needs to be a 90 degree there. So remember, if I want to find the component of W in this direction, remember what I told you? You say, what angle does W have to go through before it is pointing in this direction that I wish to resolve it in? It needs to go through theta. So the component down here will be W cosine of the angle I have moved my force through before it is pointing in my desired direction.
Yeah.
So this is something we touched on last time. If I have a force F and I wish to resolve it in some direction that is at an angle alpha, then this force has a component F cosine of alpha in that direction. If you recall from last lesson. Good. Very good. So therefore, if I'm looking at these, then it'll be W cos theta times L over 2 would give me the moment about X.
Yeah.
Are we okay? So this can be written as W times L over 2 times cos theta is equal to the moment about X.
Yeah.
You okay with that? This here, a little bit of mathematics coming in. This represents a cosine function. And what does a cosine look like? Did you remember learning about trig at GCSE, where you learned that a cosine looks like this?
Yeah.
And you learned, so that's a cosine. And this is 0. Yeah, that's 90. Oops, that's 360. Okay. Like so. Okay. And the sine graph looks like this. So we know that it's going to follow, because this W is fixed, L over 2 is fixed, it's going to follow what a cosine looks like, because these two things are fixed. So it's only cosine of theta that's going to change. So it's going to look like a cosine theta. You were right in that, Conrad. You made the right feel. You said, well, I'm going to go for C, because you realized at 90 degrees, there is no moment. Why is there no moment at 90 degrees? Well, because the weight has got no perpendicular distance from X.
Yeah.
The perpendicular distance from X when it's vertical is 0. So the moment is 0. So you knew it had to be this or this. The only piece of information missing was you didn't know what shape it would take in between that point and that point. Okay, but at least now you know. Super. Next one.
Let's just go to 9.
9. 9. Here we go. All right, we're approaching your much loved subject of electricity from the little things. Okay, number 9, when you're ready.
Number 9. A 0.3 kg mass is hung from a spring. The length of the spring is now 16. 17.5 on an additional 0.2 kg mass. Spring obeys her claw. What is a force constant? Force constant is K. Yeah. Force. I guess. Would oh god, I don't know, because when you do the force, it's not the, would it be the change in
absolutely right, and we go to our toolbox here. So we say we know that Hooke's law, this would be our starting point. That's our
so the extension is 1.5 centimeters.
Very good. And so I'd say if I want to find K is given by force over extension. But because it's per meter, yes, my extension is 1.5. I'm going to have to change it in meters.
We'll have to put it in centimeters.
Correct. So I'm going to have to divide that by 100. So I know my E. My force.
And the force, well, I guess the force is, would you do 0.2 times 9.8?
Spot on.
1, because that's sort okay. So would the answer be C?
Correct.
Okay, that's 1. And then I guess we can try and quickly fit one more in. Let's just do 9.
I'll give you
8.
I'll give you a little bit of time anyway. I'll give you 10 minutes extra because we spent the first 10 minutes just trying to catch up on how you're doing and everything else and all this.
Thank you very much. That is very useful.
That's cool.
The diagram below shows an electrical circuit. The resistance of each resistor is shown. All resistors are made from the same material. In diameter and velocity. The charge carrier. The charge carriers. E equals I over N E A. And that is
cunning little question this actually, and I'm looking at it now. It's a cunning little question. Okay. So they've told us that. Okay, yeah. I was looking for that piece of information. Okay, yeah. Mm, 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 okay.
And two. So
Now looking at this, okay, I'll let you go through it and then we'll have a quick discussion.
oh, but that's in Oi.
Don't worry, and this is one of them ones where I wouldn't spend too much time. If I spend a minute and 15 seconds and I can't get to it, I am saying, right, go for a guess.
Is it A?
You're absolutely spot on. Well done.
Excellently
done. Excellently done.
That was basic. That was not even funny how I got that. I don't even know what I did.
What did you do to get that?
I was just randomly doing reciprocals of things, and I was like, I see 0.4. I'm just gonna go for it.
Yeah. If you're really in an extreme situation with these, the easiest way to do them is to put numbers. In all honesty, literally just go, okay, first you give me some information, the one drift velocity. So obviously you're going to start thinking about Ni equals nave, yeah? And then they've told you, okay, the diameter is the same, so area is the same. What else is the same? Charge there, charge density is the same. So if 1, 2, 3 quantities are the same, it means that I is directly proportional to V.
Yeah.
So whatever proportion the current changes by, the drift velocity will change by the same proportion.
Yeah.
All these things are constant. 1, 2, 3 things are constant.
So because I did I did 200 to the -1 plus 300 to the -1. Then I did that answer to the -1. And then I got I did 300 over that answer.
Yeah.
And then I believe I did the reciprocal of that again.
I see what you're doing. So you use ratios, but reverse ratios, because you know that more current is going to be going through the 200 ohm than the 300 ohm. I've got what you did. Yeah. That would work. That works equally well. Yeah. Good.
Okay.
Yeah, sweetly done. Number 7 then, because it's now pretty much calculation. We have no choice but to just take up what comes our way.
Yeah. Oh gosh. Proton has a kinetic energy.
You can use your data sheet if you're a bit stuck on this one.
Yeah. Quantum. Okay. I guess we'll need the mass of photon, which I think is 1.6.
Please. So of a proton. Thank you. I nearly
thought proton.
I nearly thought you said photon, and I was going to say no. Photons are massless.
Oh no. Yeah, because they don't have any mass.
Proton. Panic is over. Okay.
Yeah. Yeah. So that is one. Okay. So it's got to be one of the answers because P is just mv. Kinetic energy is half mv squared. And we just want so I guess we'll just that's 2 times Would it be C?
You're absolutely on the money. Now, I'll give you another formula to remember that's worth, because the examiners love
Yeah,
to
probably.
with it. Normally, in your data, this is what you're going to see, isn't it? H over P or H over MV.
Yeah.
This is what you have in your data sheet, right? Another way to write this formula, which is what the examiner most likes meddling with, not this. They know this is easy. Yeah. And you're not going to remember this other formula. So if you can remember this formula, root 2 MEK. These are the same.
Okay. Right. Yeah.
So root, in other words, root 2 MEK is the same as momentum. So if you know the velocity, if you know the kinetic energy of an object, by multiplying it by its mass and timesing it by 2 and square rooting it, you can calculate its momentum. So it's a little trick worth remembering. Okay.
Awesome.
Good. Yep, absolutely excellent that you got there anyway. Okay, 4 and 5. Let's running through those.
4 and 5. Okay, let's do 4 first.
Cool.
Oh, this one's an interesting one.
Very interesting. Very interesting.
Initial kinetic energy of 100 electron volts. Initial speed of 5.9 times 10 to the 6 milliseconds. Accelerated for a potential 250 volts. What's the final speed? Ooh la la.
Break down the problem if it seems too chunky. Try and break it down into bite-sized chunks.
So I guess I can use half.
1 second, I won't be too long.
Yes, you can make it work with that. Would you use the equation W equals VQ for this, or?
Well done. Absolutely well done.
Okay.
That's crucial to to cracking this one.
And Q equals the final initial speed. Now where do I use my equation? Oh, could I potentially use it? That's interesting.
Don't worry, because by this time now, you know that a minute and 15 seconds would have passed by. So you'd be going, right, time to toss a coin and do the iki ponky business and see which one drops on, okay? Worry not. I'm going to tell you how to do it, because this does feed into what you got to do into year 13. So it's quite, and we've not been looking at questions like this simply because of the topics we've had. I mean, we've only had a few lessons.
What topic does this fall under?
That's a very good point. This really falls under De Broglie's wavelength. So quantum.
Oh, I see. Yeah. Oh, because our teacher said there's not going to be any quantum
Okay, so quantum not in the sense of the photoelectric effect, but quantum in the sense of wave particle duality, de Broglie's wavelength.
Yeah.
Yeah. So if he's saying there's not going to be any de Broglie's wavelength, then you shouldn't have to worry much. But just to give you a bit of an insight into this,
yeah,
a little diagram does help. So the kinetic energy it's got here is equal to 100 eV. Now, 100 eV is not good enough to help me calculate the speed. Yeah.
Yeah.
So I'm going to have to express this in joules at some stage. Then it's given an additional input of energy. Additional energy above 100 eV is given to it. And how much of this energy is given to it? Well, I'm told it is accelerated, and there we go, accelerated through a potential difference of 250 volts. Now, you mentioned to me that, hey, I know that energy given or work done as it's being accelerated is going to be equal to QV. Yeah. So in other words, if something has been accelerated through 250 volts and it's an electron, the energy it gains is 250 eV. That's why we like using the electron volt. So if an electron has been accelerated through a potential difference of 5 volts, the energy it will possess will be 5 electron volts at the end of that acceleration. If it's been accelerated through 10 volts, the energy it will possess at the end of that acceleration, or the extra energy will be 10 eV above what it had. So here, if it had 100 eV, an additional 250 electron volts has been added to it. Is that making sense?
Yeah.
Good.
Yeah.
So the total energy it will have is 250 plus 100 eV. So it's going to have a total energy of 350 eV. But this here is not in joules, so it's not good to me to help me calculate speed. I need to change it to joules. How am I going to change it to joules? How can I change 350 eV to joules?
You would do energy equals what do I always forget?
You're right, it's the right one here. Energy equals charge times voltage. Yeah, absolutely spot on. 1 second, I've just got a really loud knock.
No worries.
Hello. Hi there. Okay, I tell you what, I'm just teaching somebody, so if I get, can you guys come tomorrow? Yeah, you talk tomorrow, yeah? Cool. Oh my days. Sorry about that, Conrad. Some window cleaning girls apparently, and they're trying to get to clean my windows today, or 4 days, but there we go. Right, back to this. So 350 eV, if we want to change this to energy, we have to take this value and multiply it by the charge of an electron, which is 1.6 times 10 to the minus 19. Okay. Now this will give me the energy in joules. And then I need to make this equal to, so 350, we're going to write this 350 times 1.6 times 10 to the minus 19 will be equal to half mv squared. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. And so from there, hopefully, you should be able to rearrange that equation and Bob's your uncle.
Would it be D?
Correct.
D, okay, yeah.
Did you follow the thought pattern and the logic that we followed to get to D?
Yes.
Excellent.
Yeah.
So if it was moving, or if it had been accelerated from rest, it means the amount of energy it would only possess would be 250 eV. So you'd simply change that and then make that, change that to joules, make that equal to half mv squared.
Yeah,
Is that
because the
okay?
kinetic energy wasn't measured in joules; it was in volt.
Absolutely, yes, because it's in electron
They
volts.
have to
Spot on.
convert it. Yeah,
Spot
right.
on.
I see.
Right. I'll let you have a go at number 5.
Yeah,
And because I realize, obviously, for the essence of time, that I will give you
yeah.
the answers for this one, and you can have a go to see if you get there. So 5 is A. Okay. Are there any outstanding ones? Let's have a look here. We've done that one. Have we done
Primary setting.
2? I'm just going to write down. I'm not going to shout them out because it'll be much easier for you then to. That's in the corner. Okay. So 2. How many more outstanding here? I think we've done most of them, really. Done that. Done that.
The frequency.
Done that. 12, 13, done that. 14, done that. Done that. This one here, homework 18. Okay. So 18 is A. So you can see if you can work to that. 19, 20, done that. Excellent. So, Conrad, all you have now left is the last section.
Yeah.
But what I would like you to do for the last section is do it under time conditions. So you only need to spend an hour on that, because we've already done the multiple choice, and I'm going to send you the mark scheme so you can put yourself under time pressure. You don't need to do it right now. Yeah, literally, you don't need to do it right now.
Yeah.
Give yourself a bit of a break because you've been at it for. I know tomorrow's going to be intense because you're not going to get a break, but just for today's purposes, it's up to you if you want to carry on or if you want to give yourself a break. But I think it'd be nice to have a little bit of a reset. And just
it's nice and early in the morning, so I guess
yeah,
I'll
as well, you can do it
thing,
nice and early in the morning. You know, I used to be that kind of person anyway. I used to work very, very early in the morning. I used to find it much more useful that way.
Yeah.
So you can do it that way. So I'll send you the mark scheme. Would you like an additional paper as well to work with?
I would love
under
that,
time conditions, just to kind of, you know,
let
me look at the questions and let me see which areas I've struggled with, and let me see if I can do an additional question type thing.
That'd be so great. Yeah. Brilliant. That'd be great. Yeah.
Awesome. Have a lovely evening, and I really do wish you all the best tomorrow. Much. Yeah, that's not. It's fine.
I will also definitely recommend you to my friends who are actually looking for a tutor, if that's something that you would.
Absolutely, I'm not saying no. I'm not saying no to that, Conrad. I'm not saying no to that.
If you're up to teaching my stupid friends, then they'll be very happy.
Brilliant. Well, at least then you guys can have weekly banter and then make jokes about me.
Exactly.
Have a nice one. I'll send you the video. I'll send you the board work, and I will also send you the past.
Thank you very much.
Okay. You're welcome. Well done today. I really like to see your thinking. You were thinking out loud. I know some problems stumped you, but hey, this is new uncharted territory for you. You've never done A-levels in your life before. You've never done, you know, this is new. So undoubtedly there will be a few teething issues here and there, but what's important is having the right mindset. And today you absolutely have the right mindset. So keep it up.
Yeah. All right. Excellent. Well, thank you so much. Thank you so much.
I want to know about it tomorrow. So please don't
I'll text you right here. I'll see how we do.
You know, even if you forget to let me know how it went, I will get in touch with you to find out how it went.
Well, thank you.
I'll see you next
week.
By the way, do you want next week Friday per usual?
Yeah, any day next week is fine for me. You tell me which is best for you, and I'll try to sort out.
I'm happy to do it as we have done it today. Absolutely happy to do it as we.
Yeah, that's Thursday. That's fine. Yeah. Awesome. Okay, brilliant.
Have a lovely evening.
Cheers.
And enjoy the bright lights of the city. I'll see you soon.
Bye.
Cheers. Bye. Yeah. Cheers. Cool. Right.